All right, so we're gonna wrap up 13.4 today. I'll have the homework assignment for you. It's at the end of this section. I'll show you those, and we're gonna start 13.5 today. Hopefully get through most of 13.5. If there's a chance, we might start 13.6. 13.5 is pretty short. Okay, but we need to finish up 13.4, which was Green's theorem, right? So let's say that I have some interest in figuring out the double integral over this region D, but this is not a simply connected region. Remember, I said if you take out the center of it, then that's not anything we dealt with. You can't shrink it down, can't shrink a curve down through that hollow part, that hole. All right, but we're going to investigate this, and we're going to get a pretty amazing result when I'm done with this, all right? And then we're going to be able to answer a pretty, like what appears to be a very difficult question. We're going to be able to do it with pretty good ease, I guess. All right, so see the region? I'm going to take that region right now, and I'm going to come in and I'm going to cut it. So I'm going to cut it here and just here. And that's going to create two regions, which I will call D1 and D2. All right? I am also going to define two paths on this object here. The first path is going to go in this direction, counterclockwise, which is positive orientation or negative? Positive orientation is counterclockwise. I'm going to call that path C1, okay? I'm going to define another path. I'm going to have to use red because I'm running out of colors here. Another path which is going to go around the smaller inside part, and I'm going to orient that clockwise. All right? Got it? And I'm going to call this C2. So I have a big region D, which I'm going to cut into two pieces, and I'm looking at two curves on that region, one that goes around the outside and one that goes around the inside. One of them is positively oriented, the other one is negatively oriented, right? Now imagine that I actually physically come in here where I cut that and pull these two apart to put some space between them just so we can look at them, all right? Now I'm not going to be able to do an exact copy, but I'll do my best. All right, the top region goes something like this. I cut it here, and then it goes like this, like that, and then the bottom one, something like this, comes over here, drops down, right, goes like that. Yes? You agree? All right, now I'm going to put some points on here. Here, 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 here. And I'm now going to label some paths on this, all right? Not those paths, not C1 and C2. I'm going to call these different things, all right? I'm going to look at the path that goes this direction, like this. Comes all the way back around, right? That's a nice closed curve, isn't it? Let's call this first piece right here, just this path that goes from this point to this point, let's call that E1. Let's call the path that goes all the way around like this to that point, let's call that E2. The path that goes from here to here, let's call that E3. And the path that goes in this little kind of circular shape here, E4. You with me? The region inside, remember, this piece in here is D1, isn't it? That's D1 inside. Now I'm going to label another set of paths on this one. And it's also going to be the same, actually opposite orientation. Hold on a second. Yeah, let's go opposite. So like this. Sorry, I'm saying opposite. Just ignore what I'm saying. I'm saying the opposite of what's happening here. So let's do it positively oriented like this. Okay? With me? I'm going to call this little piece from here to here, call it F1, call this F2, call this F3, all the way back around F4. Okay? We all right with this? All right. What I'm interested in is the double integral. I'm going to use Green's theorem here. The double integral over d, partial q with respect to x minus partial p with respect to y. That look familiar? Yes? That should be equal to the double integral over d1 of the partial q with respect to x minus partial p with respect to y dA, what? Plus double integral over d2 partial q with respect to x minus partial p with respect to y dA. We agree with that? That's just the fact that when you do a double integral over a region D, that if those regions are connected together, you can do them separately, right? So that's fair. But by Green's theorem, this integral right here, just this one, this double integral, should be equal to the line integral, right? Green's theorem, the line integral along the curve that encloses D, as long as that curve is in the positive orientation. So notice that this is positively oriented, right? So this right here, just this, should be equal to the line integral over this whole path. But since I broke it up into smaller paths, do you agree I could say line integral over E1 of, what is the formula? P dx plus Q dy. All right? Then plus, hold on a second. Yeah, E2. So I'm moving here to here. Now go around here. That's E2. So plus integral E2 P dx plus Q dy plus what? E3, E4, right? To save room, I'm just going to put integral E3 blah plus integral E4 blah, right? Same thing I had over here. All right, that's this one. Plus this one, which should be, now I'm moving around D2. Here's D2. It's positively oriented, right? So I move around that one. And when I move around that one, I'm going to have line integral over what? Let's start at F1, okay? F1 of the same thing, right? P dx plus Q dy. So blah plus what? F2 blah plus F3 blah plus F4 blah. Yes? Everyone agree with this? All right, anyone see anything interesting in here? I'll give you a hint. Do these cancel? Do these cancel? They're opposite directions. Do you notice that E1 is the opposite direction of F1? In line integrals, if you change the direction, you get the same answer but negative. So this integral right here over this path should cancel out with the one over F1. And E3 should cancel out with what? F3. And what's left is pretty amazing, I think, if you see it. What is E2 and E4, right? That's what we have. F2 and F4. So let me do it this way. I have to erase here. Remember, that's what we're looking to get, right? That's what we wanted to see what it turned into. This should be, I want you to look at E2 and F4. What's E2 and F4, those two paths put together? Which is C1. That's the outer one, right? That's C1. So this is just the line integral over C1 of P dx plus Q dy, right? Plus, now, what's the others that are left? What's E4 and F2? Where is it? C2, right? It's this right here. E4 continuing on to F2 gives me C2. Understand? P dx plus Q dy. That's it. Okay, now that may not seem like a big deal, but it's going to help us out here quite a bit in just a second. What it's saying, what this whole derivation is saying, is that if somebody gives you a region, right, and you have this curve that goes around it, and you punch a hole out of the middle of it, and you have another curve that's oriented opposite, right, that the relationship between the double integral over this region and the line integrals enclosing the two little loops here is this. Okay? That's pretty cool. All right, now let's move to the example. Now I put that in my notes, okay? In the notes that you print offline, but I did it a little different in my notes online, and it's harder to follow, I think, than what I just put up here. I hope. If you've looked at my notes, I don't go in as much detail with the notes. I don't break it up as E1, E2, E3, E4, F1, F2, F3, F4. So it's harder to see that cancellation happening. I just kind of say, hey, look, these cancel, they're opposite directions. So just remember this, all right? Now, how can we use that result? So look at this question. Show that the line integral of the vector field f dot dr, which could represent work, right? This could represent work. It's not necessarily in this problem, but what is the line integral of the vector field f dot dr over the curve C, right? Show that that is equal to 2 pi for this vector field where C is any closed path enclosing the origin. So that's saying if I take the xy plane, here's the origin. If I draw any path, right? Any path. Ooh, I need to throw that away. Okay, heads up. All right.
Better be good.
Oh, that was total luck. See, I kind of stretched out first. All right, so if I take any path, any closed path that encloses the origin, that if I do the line integral over that path, it's going to be 2 pi. But the key word in the problem is that you're supposed to show this happens for any curve. So how can you possibly ever do that, right? I mean, you can't check all the curves that enclose the origin, can you? You can't. I'm about to use what we just derived a second ago, all right? And here's the way I'm going to do it. First of all, let's just call this path C, all right? And I'm going to have positive orientation on this path. Let's call this C. I'm not going to call it C1, all right? I'm just going to call it C. That's this path. That is an arbitrary path, right? Then I'm going to come in here and very cleverly, if that's a word, I'm going to choose a positive number, A, such that the circle with radius A is inside C. Do you think I can do that? If somebody draws a curve, right, any curve, where the origin is inside of it, but not on the edge of it, right? Can I choose a small enough circle so that I will be inside that curve? Yes? Because, yes, the answer is yes. And the reason is because if this curve does not touch the origin, then there's some gap between the origin and the curve, right? And I can always choose my A to be half that distance. And I'm never going to run out of positive numbers that are greater than 0, right? So I can always fit this little, later on if you actually study math, we call these little epsilon balls. If you can fit a little epsilon ball inside of here, then I can do it, right? Yes? No one's going to argue with me on that?
What if it's on the curve? Or like the curve goes through the origin?
Okay, so that's why it says it encloses the origin, and what we mean by that is that it is not on the curve itself. It doesn't say it explicitly, but just so we understand, that's what they mean. All right? If it lives on the curve, that's a different story. The origin is on the curve. Okay, so let me draw this little circle that I'm going to put in here. And just so you can see it, the A might be smaller, but that circle's right here. It has a radius of A. You with me? I'm going to orient that the same direction. I know in the previous thing where I was deriving the formula, it was the opposite direction, but I'm going to do this in the same direction like that. And I'm going to call this C. You want C1 or C2 or C sub A? What do you want? C1? I heard C sub 1 first. Is that okay? So we have C is the big one, right? That we started the problem with. It's an arbitrary curve. And I'm coming in here and I'm constructing a smaller circle inside that curve. With me? Okay. What can I do next? Let's talk about what the line integral over C of f dot dr plus, let's just look at what this is, plus negative C1 of f dot dr would be. I do realize I put a negative here. That means I'm going to reverse the direction. Okay? Well, this, by the definition of this is C P dx plus Q dy plus this C1 of P dx plus Q dy. Do you agree with that? If you did the bonus problem, you know, I think, that this is equal to this. Okay? That this is equal to this. And can you tell me what that is? So look, what does negative C1 look like? It's the same curve, but the opposite direction. Do you agree with that? So everyone agrees it's that in the opposite direction. Isn't that what I just had on the board a second ago? Didn't I do that? If you had this region D, I cut out a circle. I said this way on this one on that one, right? And we said that this really makes this equation true. It says this was C1, this was C2. Said line integral over C1 of blah plus line integral of C2 blah would be equal to double integral over D, right, of the partial stuff. Well, this C goes positively oriented. This negative C is negatively oriented, just like in the formula here. So shouldn't this turn into Green's theorem? Yes? Yes. Okay, so keeping that equals going, okay, keeping the equals going here, this should be equal to the double integral over what? The entire thing, right? The entire thing, that's D. right? Or is it without the circle? Hold on. I did too much. What was D in the last one? This right here. D was the region between them, sorry. Yeah, so not including this, right? Y'all okay with that? Of what? Partial Q with respect to X minus partial P with respect to Y D A. Yes? We're all good? Okay, now, still, I mean, I don't think it's obvious from what I've done why I've done it, right? It's just watch what's going to happen. Why would I have looked at this to begin with? It's only because I realized that I derived that formula before and I need these paths to be in opposite directions and I want to try and get to Green's theorem. But this may turn out to be a disaster. So I'm going to leave this right here on the board. This equals that. Can we do some partials real quick? What is the partial of Q with respect to X? What is partial of Q with respect to X? You have to do a quotient rule, don't you? So I'm going to do that right here. Partial of Q with respect to X is equal to derivative of the top times the bottom minus the derivative of the bottom. 2x times the top all over x squared plus y squared. Are y'all all right with this? Seems like I lost y'all there. Right, this? Oh yeah, squared. Okay, what does this thing turn out to be up here? You have x squared plus y squared minus 2x squared is what, y squared minus x squared? You agree? Okay, that's what this is. Minus, what's the partial of p with respect to x, with respect to y? Partial of p with respect to y. I'll do that here. So derivative of the top, -1 times the bottom, x squared plus y squared, minus derivative of the bottom with respect to y, 2y times the top, -y, over the bottom squared. And what does that top one turn into? Y squared minus x squared again. So these are the same. And I'm subtracting them. I'm supposed to take this one, subtract this one. So this is what? 0. And the double integral of 0 is 0. Okay. Now this is pretty awesome because this means that this plus this is 0, right? Holy shit. That means that this plus this is 0, which means that these are the same. I mean, sorry, they're opposite in sign. Sorry. You can just move this one over, right? So I'll do it. The line integral over c of f dot dr is equal to the negative of this, right? Yes? But taking the negative of this is the same as reversing the direction. Yes? So why don't I erase that negative and make that that? Yeah? So what is this telling me? If I want to know this line integral over some arbitrary c, which I never told you what it was, it's the same as the 1 over c1. But that was just a little circle. Now, it only works for this particular vector field. This is not a general conclusion that we're drawing. It's for this particular vector field we're able to do this. And so I think we might be able to do that pretty easily. Let's see if we can, right? Let's see if we can actually do this one. Yes?
Why just this one?
Why is it only working with this one?
Yeah.
Because that's 0.
Oh,
If those partials had not turned out to kill each other off, this wouldn't help us at all. Which is why when they tell you in a problem like this to show this is true, most likely when you go to Green's theorem, you're going to get zeros, or you're going to get 0 to come out. Okay, so I am trying to find, right, this whole problem of trying to show you that this line integral over an arbitrary curve is equal to 2 pi has reduced down to me showing you that over an arbitrary circle of radius a, the answer is 2 pi. So I just need to know this. What is the line integral over C1 of f dot dr? So how would you like to do this? You have options. You want to define C1 as a curve? So let's draw C1. To draw C1, I use a vector function, right? What? What's the radius of that circle? A. So A cosine t, A sine t. That should draw me the curve. T, of course, is bounded between 0 and 2 pi. So that'll draw me that circle, radius A. Now, I think what you're doing, from what I'm hearing, is that you're going to go in here and go 0 to 2 pi. You're going to take the vector field, you're going to plug in r of t, and then you're going to dot that with the derivative of r of t, or of r, and then dt. I believe that's the formula that you're using here. Okay. So we need the derivative. The derivative of r is what? Negative a sine t, a cosine t. You with me? And we get to plug that in, right? We get to plug the r into the vector field, and we need to plug the r prime into this. So here I go. It doesn't look nice, does it? Doesn't look nice, but it's going to clean up pretty good. Equals integral from 0 to 2 pi. And then the vector field with negative y. What's negative y? Negative a sine t. Over, what's x squared plus y squared? If you take these two, square them, and add them together, you'll get a squared after you use Pythagorean identity. So you're just going to get that over a squared. And then there's no square root, right? We're good? Oh, yeah, OK, you canceled already. Yes, I'll do that in a second. Now the x over x, so a cosine t over a squared again. And then I'm going to dot that, vectors. My angle bracket there is wanting to be something else. OK, and I dot that with the derivative, which is negative a sine t, and then a cosine t, and then dt. And I think we're going to get a really nice result here. When I do this one and this one together, negative a times negative a is a squared sine squared t over a squared, which is just sine squared t. And this is a dot product now, right? So I'm no longer going to have a vector. So I have sine squared t plus, and then same thing happens here, right? A squared cosine squared t over a squared again, doing this one times this one. And the a squareds cancel. You're just with cosine squared t dt. But that's just integral 0 to 2 pi of 1 dt, which is t evaluated 0 to 2 pi, which is 2 pi. So this is a really good example of how something like Green's theorem, although it's nice and we've seen it's useful, if you use it the right way, you can take a problem that seems impossible to do and do it, right? Now, a lot of times in classes that you would take like physics or down the road, a lot of times these results are known. So like for particular vector fields, you know that if you go along any closed like loop, you know that the answer is going to be 2 pi. And they more or less provide that to you rather than derive it for you. And so in this class, what we're doing is we're trying to derive where it comes from. Yeah? Okay. All right, moving on. That's the homework. There is not going to be a homework problem like this. I'm not going to give you a test problem like this. This is just to show you kind of the power of what we can do with the Green's theorem. I think that's like the first time I've ever run through that without making any mistakes. There's a lot in that to have to regurgitate. Got that? Okay. The next section is pretty short, it's pretty clean, and it's very visual, all right? I try and make it visual because I think these are two of the coolest things that we can see in this class. It's this idea of curl and divergence. So we know that we have these things called vector fields, right? And if you look at a two-dimensional vector field, that basically says like a flat sheet of paper, at every point there's a vector that points in some direction. And in three-dimensional space, the same thing. So before I talk about these two things called curl and divergence, I wanted to just mention, just look at something visually. I was going to try and give you, bring in an example to show you, hands-on thing. But let's just imagine that we're looking from the top down, and we have this pivot point, and we have this piece of wood, all right, like this, all right? And let's not look at like gravity is down or anything. Let's just say there's no gravity. In fact, we're looking at it from the top, so gravity wouldn't matter. But if I push on this with a force here and a force here at the same distance from the pivot point, and I push with the same amount of force, what's going to happen? No, this is a pivot point, and it's locked in place. Okay, that doesn't move. Well, let me do this. What happens if I just do that? Start spinning, right? It would start spinning this way, yes? Or if we want to look at this almost like a paddle wheel, and you turn on a fan over here and you start blowing, and this will start spinning, won't it? But if I put a fan over here and start pushing with the same amount of force that direction, it's going to be stuck, right? It's not going to move. Okay, and if I do something like this, where I push with a lot of force right there, but then I put, a little bit of force over here, that still might bounce out and it still may not move, right? Exactly, like torque. So the idea here is that all I want you to see is that this picture, I'm about to show it to you in an animation, but the idea is that we have forces pushing on this paddle wheel, all right? And we just need a basic understanding of what happens. So let's talk about curl. The first thing is to understand that we are defining in this section 2 operations on vector fields. So if someone hands you a vector field, we have these 2 things called curl and divergence. Curl, when we take the curl of a vector field, okay, when we do that, the answer is a vector. When we calculate what's called the divergence of the vector field, we're going to get a number, a scalar. And what they mean is what I'm going to try and show you, all right? And then I'll show you how to compute them. Or you know what? I'm going to show you how to compute them first. Well, what do you want to see? The computation, or you want to know what they are first? Yeah. You want to know what they are? Okay. Curl. I'm going to do the 2-dimensional curl first. Okay, so let's say we have this vector field here, right? This is our vector field. So you can tell that, in the middle, as we move away, right, as we move to the left or to the right, those force vectors get stronger. but they're all pointing in this direction, right? So right now, do you see that my paddle wheel is not moving? That's because the force on each side of the paddle wheel is equal. So what I want you to do is imagine that we're actually looking at a point. We're looking at a single point, and imagining these little, like infinitesimally small paddle wheels, and we just kind of stick them out and we see what happens. If we stick them out and nothing happens, the curl is 0. Curl meaning like twisting, all right, turning. So I don't want to twist. What's going to happen if I slide my point to the right? What's going to happen? I should start spinning which way? Clockwise? Let me try. Okay, you see that? Clockwise rotation. And I'm having the computer calculate the curl for us, which I haven't shown you how to do. Notice that our curl is negative. Yes? Clockwise, negative rotation. Then what would happen if I go to the other side? Should be counterclockwise, right? And my curl is 1.8. Now, watch what happens if I move this further to the left. What do you think is going to happen? Things will start spinning faster? So same direction? Same speed? Let's see. Look, 3.08. The curl got bigger, right? And it's positive, so I have counterclockwise rotation, bigger number, faster spin. So I like to kind of think of this as almost like, think of, if you can, a flat river, okay? This like sheet of water flowing. And let's say it's, how deep is the water? It's only the depth of like one water molecule or something, all right? And so this water molecule is right here. All these other molecules of water are moving down the river with it. So if this little water molecule is going down the river, right, and he kind of sticks his arm out, the guys on the right side hit him, right? The left guys hit him, but not as fast, so he starts spinning as he's going down the river. And so he has this twist to him. And does that make sense? Okay, and so that's the curl of the point. Okay?
That was a nice spin too.
You like that? Okay. And then what if I move him up? What if I move him up? Nothing should happen, right? Yeah, the curl's exactly the same, 3.08. Initial settings. Go back to the beginning. All right. Now, what if I change the vector field? So that was this. By the way, this was the vector field. I have it where you can change them. Let's do a more interesting one. There we go. So if I start moving, right now I have 0 curl. If I move this way, I'm getting positive curl. If I move up, negative curl. If I move up, changes a little bit. Did y'all notice that the wheel does spin faster when it gets bigger? You don't understand what it took to make it do that. Oh, did I stop there? I had almost 0 curl there. Look at that. Right up there, I'm getting almost 0 curl. It's turning. I don't know if you can see it turning. I'm going to draw a line right there. Y'all do see it turning? It's very slow, right? Very slow. All right. Understand geometrically the idea of curl. Okay. This is stuff you would use in like fluid dynamics, right? You want to know how your fluid's behaving. Is everything chaotic and spinning around, or is everything just kind of chill, sitting in one place, not wanting to twist? All right, I'm going to pause this because sometimes I bring my computer to its knees. 3-dimensionally. Oh, you know what? Go back to this. I told you that the curl was a vector, right? Okay, right now you can't tell it's a vector. And this right here is actually the magnitude of the curl. I should have told you that. This is the magnitude of the curl. The curl is actually a vector, and the vectors is coming straight out at you. In 2-dimensional, your curl vector is always coming right out at the board, all right? The length of that curl vector is going to be a measurement of whether or not, or how fast it's turning. If it goes into the board, the rotation changes the other way, all right? But in three-dimensional space, all right, so you see this little thing up there in three-dimensional space? What that is a point, all right? The red line segment there is the direction of the curl, all right? And that yellow disc is the paddle wheel. So I'm not going to show you the vector, well, I can show you the vector field. There it is, but it gets in the way. Is it moving? I have curl. Is this playing? Oh, play. Okay, here we go. So if I let things go, if that point, if that was a water molecule, now you're in a river and the river has depth and three-dimensional and you're a water molecule moving around in here, then if you were right there at that, instant moving, you would have this sort of twist to you like this, right? As you moved. And so you would ask, okay, what happens if I change my placement somewhere in that field? Trying to get to a negative curl. It's slow because the computer is doing a lot of stuff right now. I don't see me getting negative curl. Oh, I'm sorry, I'm taking the magnitude of it. Oh well. You just have to deal with it. I think you get the idea. Oh, that seems a lot faster, right? Right? So you get more twist there. All right. Where are my computer science people? Any computer science people? There you are. All right, here you go. So there it is. That's not so bad. The hardest thing that I had with this damn code was getting it to draw an arbitrary circle. Circles drawn, if I tell you to draw a circle on a flat sheet of paper or this wall or on the ground, that's easy to do. But to draw a circle arbitrarily in space is difficult. It requires quite a few transformations to do it right. So, yeah. That's just encouraging for you later. You like code, there's code. All right, I think that's all I have. So let's actually get to the computation of curl. Well, the computation for curl comes from, we're going to use a cross product, okay, to define what curl is. But before I can define cross product, we're going to define this symbol right here called del to be equal to this. And it's right there, but I want to write it down here. This is different than anything you've ever really seen before. Because if I give you a vector, usually you want me to plug some numbers into that vector, or usually you want that vector to have like functions in it or something, right? Variables. This is a vector that we are defining to not be any of those things. The first component of this vector is what we call a differential operator. It's an operator. It operates on functions. You put this together with a function, and it takes the derivative of it with respect to x. You put this together with the function, it's going to take the derivative of it with respect to y, but it's not true multiplication. Do you see that? It's not like 2, 5, 7, then you just multiply numbers. That's not what's happening. You're operating. This tells you what to do. So this symbol represents the del, which is the differential operator. Okay. So curl is defined to be, curl, the way we write it, curl f, is defined to be the del crossed with the vector function f. And here's the standard notation for it. Del cross f. And we know from cross products that when we do cross products of two vectors, what we like to do is take the first vector, put it here, the second vector, put it here. And then this is our i's, j's, and k's. And our answer should be a vector. So to figure out the first component, we cover up this, right? And then we do a determinant right here, right? And then we cover up this and do a determinant, and then this and determinant, right? By the way, P, Q, and R, it's up here in the notes, are the component functions for the vector field, P, Q, and R, as they've been for a while now. Yes?
The order number,
What order?
like it's del, cos, theta. Doesn't matter, or it can be either way. Like S cos del.
You should get opposite signs, so this is the order you want to go with. There'll be parallel vectors. They'll be pointing in the opposite direction, though. So, but this is what I'm kind of making sure you understand. When I do this first computation, I do determinant, we say this times this, right? Do you realize that's not this times this anymore? It's the partial derivative with respect to y of this. So that's what this is. Minus, so going this way now, we normally say this times this, but again, it's not multiplication. It's the partial with respect to z of this, which is partial of q with respect to z. Understand? And then you keep going and finish off the rest of it. It's computational. There's no magic here. Or you just got to know how to do cross products and take derivatives. So let's find the curl. Find the curl of this vector field, and then find the curl. Then find the magnitude of the curl at a specific point. So the curl of f will be equal to del crossed f, which is equal to this thing, I hat, j hat, k hat. By the way, in the homework solutions for this section, which I posted today, I don't write I hat, j hat, k hat. I just do the two vectors. But following the book's notation, that's what they do. So this xy squared, no, hold on, oops. Let me give myself a little more room here. I need my del first. So del would be partial with respect to x, partial with respect to y, partial with respect to z. And then x squared yz, xy squared z, and xyz squared. Why don't you try that? See if you can get it. Okay, that enough time? Y'all got it? Okay. Try and do it without writing each one of them down like partial of this. Like do the computation if you can. You know what I'm saying? Like if I do the first one, I'm going to do the partial with respect to y of this. Like do that mentally, if you can. When somebody gets an answer, let me know. I'm writing down on the board what I told you not to do, just so that we have something to reference if in case, just in case. Anybody get that? Yes? Okay, that's your curl. Now, what is the magnitude of the curl? Well, find the curl and its magnitude at a specific point. So now, if someone tells me x, y, z, what I'm doing is I'm actually going to find, in three-dimensional space, if you go out to that point, I'm finding that red line segment, and if I take the length of it, it tells me how fast that yellow wheel was spinning. Okay? So that's my symbol for at. At the point 2, 1, 0, we have that the curl of f is equal to, it's a vector, 2, 1, 0. What do you get if you plug in 2, 1, and 0 for x, y, and z here? Negative 2, 4, and 0. Agreement? Okay. And then what is the magnitude of the curl? Root what? Root 20 or 2 root 5. Okay. What do y'all think? Pretty straightforward, just a computational thing? All right. I did a couple of those on your homework, and one of them very straightforward like that one. The other one was a little ugly, but I did work the whole thing through. All right, so what about finding the curl of this? And find the curl and then find the magnitude of the curl. What should you scratch your head about initially here? Yeah, didn't we say cross products, to do a cross product you have to have a three-dimensional vector? Yes? This is only two-dimensional. So how can we do it? So what we'll do is we're going to extend this vector field into 3 dimensions by making it a function of x, y, and z. I'm going to leave the x and y components the same, and by default, I will put 0 for the z component, and that's what I will always do if I want to extend a two-dimensional vector field into 3. That just basically flattens it out on a sheet of paper, which is where you were to start with. And then you can do your curl. So curl f, I think this one's going to go pretty quick. I'm going to write my notation this time the way I did it on the homework. What's the curl? Cover this up. Partial with respect to y of 0, 0. Take away partial of x squared with respect to z. Just 0. Sorry, I didn't see negative x squared. Just 0, right? Because you're treating negative x squared like a constant. So you're getting 0 there. And then when you do this one, 0. And when you get this one, negative 2x, so negative 2x. All right. What's the magnitude of the curl? Square root of 4x squared, which is actually the absolute value of 2x. Okay. Do you recognize this vector field? It's the first one I showed you where the arrows were going bigger on the outside, smaller on the inside. Do you remember at the center that I wasn't spinning? So when x is 0, what's my curl? 0, 0, 0, the 0 vector, right? Which means I don't have any spin. The magnitude would be 0, no spin. If I moved out to the left, right, it got bigger, curl. So you can see if I put a bigger x value, either negative or positive, I'm going to get a bigger curl, yes? But notice when I moved up and down, do you remember this? Nothing changed? You see how there's no y in here. So this curl is independent of y. And you can see it in here now. We've already interpreted it geometrically. Let me make sure I stop that thing from spinning. Okay. Definition here, it's kind of hidden in here. But in fluid dynamics, all right, this curl represents the tendency of the fluid to rotate, right, which is what I tried to already explain. If the curl of your vector field is 0, then there is no rotation, and the field is called irrotational. That word look familiar? I think that word's on your take-home test.
Yeah.
It is. This just talks about extending the vector field, like I just said. If you extend a vector field from 2 dimensions to 3, you just always let your z component be 0. Now, a major, major result of curl. Do you remember that if we had a vector field in 2-dimensional space, that we could check to see if it was conservative or not? And what we did was we calculated this and we said, are these equal? Remember that? But I said we could not do that in 3-dimensional vector fields. We now have a way. And here's the condition. That's it. That's all you need. If your curl is 0, if the curl of your vector field is 0, it's a conservative vector field. So everywhere in the field, nothing's rotating. Things can be moving, but nothing's, no little molecule is spinning around as it's moving. It's moving in the direction it's supposed to go without any influence from anything around it trying to spin it around. That's a conservative vector field. That's an awesome way to check vector fields, but you still have to calculate a curl, which is a cross product, and those can be a little bit buggy sometimes. Now let's talk about divergence. Divergence is another operation on vector fields, and we'll talk about what it means first. We'll show it to you. I have 2 ways of showing this. So for this one, I want you to look at, this is the same vector field we had earlier, right? That 0, negative x squared. We know that if we take this point and do little paddles, we can get this spin. That's curl. Divergence is something completely different. What it does is we try and imagine we're at a point, right? And we try and imagine opening up this little infinitesimal ball, this little epsilon ball like I was talking about earlier, just really like infinitesimal ball. Now I've zoomed in on it. Here it is. If I look at all the points around this ball and pick some points, there's a vector at each of those points around the ball, right? There's a vector from the field. Here are all the vectors on that field. I've labeled them in red if they are going into the circle. I've labeled them in green if they are going out of the circle. So what does it look like to you? Looks like the amount going in is equal to the amount going out, right? And so they should cancel each other out, and you should get nothing. That measurement of how much is going in and how much is going out is divergence. But the ball, this little circle, remember that circle is actually infinitesimal, right? When you get to a single point, you can't really talk about going in and going out, right? But we can do a limit kind of, and that's where this idea comes from. So if I make this ball bigger, so it's easier for us to see it, all right? And we got the same going in and same going out. Now what's going to happen, what do you think is going to happen if I move this to the right? Do you think I'm going to have the same going in as the same going out? I don't know, let's see. You have your own guess. Ah, so what happened? They got longer. It's because the vectors over here are getting longer, right? But they're still canceling each other out, aren't they? Because the ones that are coming in are as big as the ones going out. So we're still getting the same divergence here. You can add more vectors if you want to see more vectors in action here. Take them away. You can zoom in if you want to take a closer look at them. And you can zoom way in. I'm just looking, I haven't looked at this in a long time to see what the hell I put together here. Okay, so this is a pretty uninteresting vector field, isn't it? In terms of divergence, it's pretty boring. The divergence is 0. It looks like everywhere, right? If I move this up, anything gonna happen? No. Move it to the left. Div is always staying the same, right? All right, so let's change to a different vector field. And let's go to the initial settings here. All right, more interesting. How about that one? You think we're going to get some interesting things?
Yes.
Let's see. Boom, right here at the origin. Oh, crap, div is 0 still. Let me see, zoom into that. Div is 0. Let me show some more vectors. No, okay, well, let's move it. Up or down? Left or right? Left. Ah, there we go. Okay, so see, we got more red coming in. Like the number of vectors going in might be equal to the number of vectors going out, but it's the length of the vectors that's overpowering what's going out. So if there's more force going in, the force coming out is not as much. So it's almost like pressure, you could say. More pressure on this side than on that side. Make sense? What about if I move it up? Oh yeah, notice the answer is negative. The answer is negative because there's more going in than coming out. Moving it up. Oh boy, we've got a lot of very long red vectors going into that, overwhelming the green coming out. You see it? Probably going to have to move to the other side. I don't know, can I get my div to be positive? Let's see, here we go. Oh, over here I've got some positive div. There we go, let me zoom back out. I moved too far. I think you can kind of see it here. More going out, the green ones are longer. That's kind of cool, huh? All right, what is this in three-dimensional space? Instead of on a flat piece of paper and a point and a little circle, it's going to be three-dimensional space, a point and a sphere, a little ball around it. Well, I took the time to go ahead and put that together a couple of years ago. Here it is. So remember, this is a point, right? This is a point. But I'm making this little ball around it, and I'm looking around all the ball, and I'm trying to figure out if I've got more going in than I do have coming out. And I'm not showing you the vector field here. Yeah, I can't show you the vector field. You just have to believe me that there's a vector field here, all right? So here it is. Oh, shit, our div's big, right? Got a lot of vectors coming out of this ball, and they're really long compared to the ones going in. Zoom in on this ball. Let's get more vectors in there. Right, you see them, all these little ones in here being overpowered by all the big ones coming out. What is that?
Looks like an asteroid.
An asteroid? Yeah. So like here we are, right? There's us right here. Yes. And we're probably thinking to ourselves, right? What are we thinking at this moment right before impact? Positive div. Positive div. Boom. It's over. All right. Let's move this thing around. Maybe we can get some negative div here. Oh, here we go. Something's happening over here in the field. Now we're getting negative div.
We're dodging.
Yeah. I think you get the idea. Yes? So in terms of, curl gave us our tendency of our fluid to want to twist, right? To turn, to curl. The div measures the tendency of the fluid to diverge or leave a point. So it's like, it's kind of difficult to explain. I know some of you have heard of divergence before. You have any other good? No? No? Okay, divergence, tendency of the fluid to diverge or leave a point. So if you're at the point, if you've got positive divergence, there's more of a tendency for things to flow away from it than there are to flow into it, right? So if you're at a point and you move a little bit off the point, most likely you're going to be moving away faster than you are going to be moving back towards it. So anytime we have this, we go to a point, if the div is positive, then we call that point a source point because things are wanting to move away. So it's like you're at a campfire, you can feel the heat coming off it. It's a heat source, things are coming out of it. So when your div is positive, things are coming out of the point, it's a source. If your div is negative, then things are wanting to go in, that's called a sink. And anytime your div is 0, it's called incompressible. And the idea is, that it, like a solid block, nothing wants to go in, nothing wants to go out. There's equal going in than there is going out, so it's just kind of static, right? Incompressible. Now the computation of div is much easier than the computation of curl. So easy, in fact, that I can just do one example and we can move on. So div, the notation for it is this, div f. It does involve del again. There's del. That's a differential operator, but instead of crossing it with f, we dot it. And we like dotting vectors, right? Dotting vectors is so much easier to do. So if I take, I don't think I have it written here, but this is del. Right, that's del. And this is f, p, q, r. Then if I dot them, I do this and this together, right? Which means the partial of p with respect to x, because it's a dot product, plus partial of q with respect to y, plus partial of r with respect to z. So it's super easy. All you're doing is taking the derivative of each of these component functions with respect to x, y, and z respectively and adding them together. And that's it. Your answer is a scalar. That's the problem we had earlier, where we were asked to find the curl and the magnitude of the curl. Remember that one? That took us a little bit. Let's do div. Div f is del dot f, which is, I'm just going to do this without writing the formula. It's the partial of this with respect to x. 2x, y, z. Vector? No, plus partial of this with respect to y. 2x, y, z, plus partial of this with respect to z. 2x, y, z, which is 6x, y, z. That's your div. So the div of this particular vector field depends on where you are, right? Your x, y, and z coordinates all contribute to whether or not you're going to have div or not. Now at the point 2, 1, 0, what's your div? 0, because the z is 0. We happy? Now, this is going to look weird. But remember Green's theorem, right? Remember Green's theorem? Yes? Green's theorem says that the line integral along closed curve C, P dx plus q d y is equal to double integral over the region D that C encloses of partial q with respect to x minus partial p with respect to y dA, right? That's Green's theorem. But this, oh, and this right here, sorry, this is equal to line integral over C of f dot dr. Do you agree with that? This is this,
Yes.
which is this. So look at this new formula for Green's theorem. If this is equal to this, right? That's equal to this. That means that this right here, oops, I thought I silenced that, must be equal to this right here. Do you agree with that or not? Yeah, what's the curl of f? Well, let's go back in the notes real quick. Curl of f. Where are you? There it is. Okay, there's the curl of f, right? If I dot that with k, because that's what that formula said just a second ago, dot that with k, what's the k vector? IJK? 0, 0, 1, right? If I dot these, the 0 kills off the first one, the 0 kills off the second one, and 1 times this is that, right? It's another way of writing Green's theorem with all vectors in it instead of having this right here. These are scalar functions, right? So that's why we call that a vector version of Green's theorem. Okay, understand? That will come into play later. And the next one for sure is going to come into play later. It's another way of writing Green's theorem. All right? And for now, what I want you to do is just remember this is here. I'll refer back to it later. I don't want to derive this. The book does it. They do a decent job. I want to spend some time. I would want to spend probably 20 minutes to 30 minutes deriving that and making sure you understand where it comes from. I'm not going to take the time. Just later on when I refer back to this, right, have a little note somewhere that says, you've got the formula sheets, right?
Yeah.
You've got this in there, all right? Now, there are a bunch of identities with curl and div. And I have one here that I'm not going to work through. I just want to show you like the basic idea behind it. If you take the div of the cross product of two vectors, it's equal to g dot curl of f minus f dot curl of g. And this is an identity. And do you remember in pre-cal when you had to show an identity, like you started with one side and turned it into the other side? That's what you would do with this. And this is in your notes. You can follow this. They started with the left side, and they turned this into the right side. All right? I think what I'll do is you almost had one of those on your take-home, but I took it off. It was the last problem. I took it off. I might offer that as an extra credit or maybe something to that effect on the final as an extra credit without ever showing you how this is done. See if someone would want to tackle that. Now, your homework assignment has a few of these. I think there's 2 of these, which I did not put solutions up for. Again, those, just realize those are going to be bonus problems, so you don't have to do those. There's the homework. I'm talking about 21 and 23 are identities. All right. That's it. We doing all right? 3-5? It's pretty straightforward, 3-5, right? It's just computations.
So just 6, 7, and 8 more?
Pardon?
13, 6, 7, and 8, that's it?
13, 6.
As far as what we have left on
Oh, yes. No, there's a section 9, I believe. maybe not. Yeah, there's 9. But section 9 is only 3 or 4 pages long. All right, we are going to start 3.6, but not heavily. I'm just going to get you going with this, and then I'm going to have a handout. We're going to start talking through this handout. Okay, remember, way back from chapter 10, look, this is a really important section, all right? I lose a lot of students right here in this section. So ask me questions. When I hand you this handout in a little while, if you have questions, let's resolve those, because if you can't do what's in this section, the next 3 sections are going to be impossible, because you have to be able to do what this section asks you to do. All right, remember from chapter 10 that if we defined a vector function r of t to be f of t, g of t, or if we do it 3-dimensionally, then this drew a curve. And I told you back then that later on we would be able to do something like this and be able to draw surfaces. And that's what this section is about. Can we draw a surface with a vector function? And the answer is yes. Okay, if we have a vector function, and this time, instead of having one variable that we're plugging in t, we plug in 2 variables, which we call u and v. I'm going to write this over here because it's going to be so important to us. If we have 2 variables being plugged in, and then a 3-dimensional vector, okay, where the x somehow depends on u and v, the y somehow depends on u and v, and the z somehow depends on u and v, then if you define it that way, and you let you put some restrictions on u and v, give them some domain restrictions, then you will draw a surface in 3-dimensional space. The book does not take a lot of effort and time in letting you practice converting a surface into that form. So that's what I would like to do now. I'd like to hand you this worksheet, and we are going to go through, and there's, I think, examples A through F, and we're going to come up with these parametric functions. It's called parametric surfaces. Go ahead and hand those all the way back. You know what? Let me get you 2 more. Whoa. If you could hand those back, please. 5. There you go. These are hard to see from the drawings. I don't believe that this is up. Someone can tell me, is there a CDF file on the website that has this? It's hard to see with what you have in your hands, so no, you can tell me later. Okay, you ready? I want us to come up with a parametric surface. In other words, a function r, a vector function, which depends on 2 variables u and v, that will draw me that circle. So let's pay attention to what's happening here. This circle lies in which plane? I did label x, y, and z on yours, right? It lies in the xz plane. So if I look at it, okay, if I twist this around like this, kind of turn it, come in like this, then do you see that I have a positive, this is the x direction, positive x direction, this is the positive z direction. And so what I need to do is just draw a disk, right? A solid disk in the xz plane. Okay, so let's talk about the different parts of this. Your x, your y, and your z. Right now, you know, because of where you are, any point that lies on this surface, the y value is 0, right? That'll flatten it out onto the xy plane. Agreed? Xz plane, sorry. We agree? So this is definitely 0. The other part of this, the x and the z, need to draw you this circle. Well, actually, it's not a circle, it's a disk. You have control of two variables, u and v. You can control them however you want. So just what does your instinct tell you you're going to need in order to draw something like that? Cosine and sine. Now we've used cosine t and sine t, right? This time we don't have t, we have u and v. So how about this? How about cosine u, sine u? If I let u vary between 0 and 2 pi, this will draw me a circle with radius 1 right now, right? Right? But I wanted to draw a circle with radius 2 and 1 and 1/2 and 1.5 and everything in between. So I want to be able to vary that radius. And I have another variable. So why don't I let the number in front of this be v, and then control v with this inequality? Do you understand how that worked? Okay. So if you wanted to check whether or not you did it right, what you could do is you could say, okay, let v be 0. Start here with v is 0. V is 0. These are both 0. That's everything is 0, right? And you get the point 0, 0, 0. Good. It's there. Then you could let, I don't know, v be 1. If v is 1, and now let u change, you draw that unit circle. If you let v be 2, that'll be 2 and 2, and then you draw a circle with radius 2. Understand? And then everything in between. I hope that makes sense. That's the easiest one. No questions. Let's look at B. Find the vector functions, plural, which yield the four face surfaces of the tetrahedron with the given vertices. So you have a tetrahedron. It has four faces on it. Since each of the faces is a surface, you have to come up with four separate parametric functions that draws each surface. Here it is. Mine looks a little different than yours, but there it is. So let's start with the easy surfaces first. Let's look at the surface. Well, you tell me, which one do you want to start with? The base of this tetrahedron, which that surface lives in the xy plane. Agreed? The base of that tetrahedron. So I'm going to draw my xy plane like we normally look at it. Here's x, here's y. And give me some points that are on my tetrahedron that I can put here. That, I believe that is a 3. Yeah, well, yeah, I gave you the vertices, didn't I?
Yeah.
I didn't label them, though?
No, but yes.
It's 3? So this point is out 3, 1, 2, 3. So this would be a 3 here. And then 4 on the y. And then, of course, the origin. So we're talking about this surface. I want you to be able to draw that. And you can control two variables, u and v. Well, this looks a whole lot like a type 1 region from double integrals, doesn't it? And since it looks like that, we did this already where we controlled, what, x and y? This was type 1. We let x go between 0 and 3, and we let y go between 0 and the function of x, right? This line. We're going to do the same exact thing, but we're going to use u and v instead. So I'm going to write this down. R of uv will be equal to, oh, is there anything about this vector function you can tell me right now?
Z is 0.
Z has to be 0. Because we're looking at the one that lives on the ground, right? So your z values are always 0? What do you want your x component to be? You want to call that u? Sure, we could have called it v also because we can control both of them. So I'm going to say this right here is going to vary back and forth. That's going to be my u. So that's this. U then would be between 0 and 3. Now I have to get control over the v and figure out how it plays into this. This is the part that most people get hung up on. What are you thinking? If this is really my u now, right? Right? That's really my u. Then this right here, my y, what is this equation for y of this line? What's the slope of it? Negative 4/3 u, right? Plus 4. That's the equation of this line. Y-intercept 4, slope negative 4/3. Yes? Here's the mistake that people will make. What they will do is say, oh, okay. Well, that tells me what my y is, right? So my y is negative 4/3 u plus 4. They put that there. Why is this incorrect? Pardon that? Pardon me?
You need to be in terms of v.
Well, it is in terms of, we haven't used v, right? If we haven't used v, then this is a function of one variable. And if this is a function of one variable, it doesn't draw a surface. It draws a curve. What curve is this drawing? It's just drawing this line. See, because what's happening is that if I fix u to be 0, what's this? 4, right? So I go 0, 4, I draw that dot. If I let u be 1, let's let u be 3. If I let u be 3, then where am I? 0. So I'm over here. I have no choice. Let's let u be 1. If I let u be 1, where am I? Let's see, negative 4/3 plus 4. I'm right there, okay? But I'm drawing the line. I'm not drawing the actual surface. What I need instead is that when I'm at u equals 0, I don't want to draw just that point. I want to draw every point between here and there, right? And when I get to 1, I don't want to draw just that point. I want to draw every point between this and that point. Yes? So what I do instead is I call this v, and I control v down here by letting it vary between 0 and negative 4/3 u plus 4. Extremely different thing happening here. Do you see the extreme difference? Okay, let's run through it again. Someone comes in right now and fixes u at 0. That's a 0, right? What's your v? Your v is going to be between 0 and, put 0 in here, 4. So when your u is 0, your v is everything between 0 and 4, so it draws that entire vertical line for you. Then you move u over, let's say we move it to 1. Move it to 1. Now my v is trapped between 0 and whatever that number was. It's going to draw everything between 0 and all the way up to that line. That's supposed to be straight. Understand? And so as I move u across, my v keeps adjusting, and I draw all the vertical lines, and I draw the entire surface. Okay. Let's see if you can come up with the parametric equations for the remaining 2 outsides. So we just did the bottom, right? We just did the bottom. Can you do this back side back there? Or the back side of that one? See if you can do it on your own. You can use u and v again. Okay, this is a totally separate surface. All right. And let's call these something. Let's call this surface A. Let's call the one over here B. And the one on this back side, let's call it C. That way we're all on the same page with this. So everyone try B right now. Anybody think they have it yet? No? Okay, you think you do? Okay. If you think you have it, try and get C. If you think you have B, you can look up at the board. That should be what you have for B. So here's what I'm going to do, because we've got about 5 minutes. I don't want to end early, but I also want you to kind of explore this on your own a little bit. I'm going to make for a take-home assignment that is due on Monday, all right, is just to do C, and there's one more surface, which we've conveniently avoided, which is this one up, that's the face, right, of this thing. That's the hardest one. I want to see how you do trying to get that yourself. Do you want any hints, or you want a couple of hints? It's a plane, and so there is a relationship between the x, y, and z. If you could figure out what the equation of the plane was, you would have that relationship. Then it's just a matter of making sure you get all this right. So I will see, everyone should be able to do C. I've shown you one. I've given you the answer for one. Hopefully you can get the last one yourself. This front face, which we'll call D, let's just call it D, which is this face right here. I'll just see what you do, all right? Say that's due Monday, beginning of class. All right, we will pick up next time. We will go through and finish off the rest of the examples on this, and then we will get into the next section, which is surface integrals. We're going to be not surface areas. We're going to be integrating where our region of integration is a surface instead of a solid. So that'll be interesting. Then we get to flux, and then the Stokes' theorem, then divergence, and then divergence theorem, and then we're done. Have a good weekend. Stay out of trouble.